Hello everyone. In chapter 7, we discussed linear regression models where the partial effect of a predictor variable on the response variable was constant and did not depend on other predictor variables in the model. For instance, when evaluating the price of a house, we assumed that an additional bedroom resulted in the same increase in the price of a house regardless of its square footage. This is unrealistic. In this chapter, we estimate and interpret regression models with interaction variables. These variables allow the partial effect of a predictor variable to depend on the value of the other predictor variables. So continuing with the house price example, an additional bedroom may have a higher impact on the house price with a larger square footage. We then turn our attention to regression models for non-linear relationships. So these models are useful when the relationship between the predictor variable and the response variable cannot be represented by a straight line. So in the house price example, an additional bedroom may have a higher impact on the price of a house when going from 1 to 2 bedrooms than from 4 to 5 bedrooms. Also, we have used goodness of fit measures to assess predictability in the sample data that was also used to build the model. But we have a problem here. These measures do not help us gauge how well an estimated model will predict in an unseen sample. So in this chapter, we will also employ something called cross-validation techniques for regression models, where we partition the original sample into training set to build the model and a validation set to assess the model. So the first part is regression models with interaction variables. So recall that the linear regression model is y equals beta naught plus beta 1 x1 up to beta k xk plus epsilon, and y is the response variable. All of the x's are the predictor variables, and the epsilon is the random error. We know that the betas are unknown parameters, and we need to estimate them. We use OLS method to estimate the betas, we get the b's. So we have y hat, the estimated response variable, is going to be b naught plus b1 x1 plus up to bk xk. And y hat is the predicted or estimated value of the response. And the b naught, b1, b up to k, these are the estimated parameters. And what we have right now, this is linear regression, and the b's measures the change in y hat given a 1 unit increase in xj, holding all other predictor variables constant. And bj represents the partial or marginal effect of x on y hat. This is exactly what we learned in chapter 7. And the marginal effect of the predictor variable, the b's, they do not depend on the values of any other predictor. And as we said, this is not realistic. We may have an interaction effect. And this may occur when the partial effect of a predictor variable and the response variable depends on the value of other predictor variables. And we are going to discuss, or we're going to give examples later, when we have interaction among or of two dummy variables, or interaction of a dummy variable and a numerical variable, and an interaction of two numerical variables. Finally, when we build the models, we are going to report again the adjusted R squared. Why is that? It's more conservative and robust measure. Also, it provides a better indication of how well your model fits the data while taking into account the complexity introduced by the interactions. After we finish the interaction impact or the interaction relationship, we are going to talk about, or we are going to have examples about having non-linear relationships. In many applications, the relationship between the variables cannot be represented by a straight line. And we can capture many interesting nonlinear relationships within the framework of the linear regression model by simple transformations of the response and or the predictor variables. And we're going to see this, how to do transformation for the response or the predictor variables, or both of them. The first part we're going to discuss is how to build a quadratic regression model. In microeconomics, you may have learned that a firm's average cost curves tend to be U-shaped due to economies of scale. The average cost y of a firm initially increases as output x increases. However, as x increases beyond a certain point, its impact on y turns positive. Other applications show the influence of the predictor variable initially positive but then turning negative, leading to an inverted U-shape. So the quadratic regression model is appropriate when the slope capturing the influence of x on y changes in magnitude as well as sign. And as you can see, the quadratic regression model with one predictor variable can be written as y equals beta naught plus beta 1x plus beta 2x squared plus epsilon. And we can extend this one to have a multiple predictor variables. Also, we can see from here that when you do prediction with a quadratic model, you're going to get this predicted or estimated model. And the coefficient of b2 of x squared, which is b2, is important. Why? Y hat, the estimated y, gets or reaches a maximum when this is negative. Why? Because if this is negative, it's going to be up and down. So the y hat reaches a maximum value. And if b2 is positive, then y hat reaches a minimum, because if this is positive, so it's going to be U-shaped. So y hat takes a minimum, or it has a minimum value. And this occurs when the value of x is negative b1 over 2b2. The third thing we are going to do, so the first model we're going to develop is linear regression with interaction terms. The second model we are going to develop is linear regression with quadratic terms. The third model, fourth and fifth, we're going to create regression model with logarithms. When we talk about logarithms, we're talking about percentages. So the first type of logarithms we're going to develop is log-log regression model. Log-log regression models are used in situations where the relationship between variables is expected to be better explained by the logarithmic transformation of the variables. Why? Because this is, in our scenarios, we are going to see the way that we interpret this. So in the interpretation of the coefficients in terms of percentages, not units. So log-log, the interpretation of the coefficients in terms of percentages change is more meaningful here. Like in this example, in this kind of model, log-log, the coefficients represent elasticities. What does it mean? It indicates the percentage change in the dependent variable associated with a 1% change in the independent variable. Again, the percentage change in the response variable associated with 1% change in the predictor variables or variable. And this is the model that it's called log-log because the y and x contains logarithmic here. How to do the prediction? We can do, or how to predict this model. This is the predicted model. Len y hat equals b naught plus b1 len x. But we still can make predictions using regular units using this formula. And again, most of them we're gonna use R to do all of this. How to interpret this, and this is important. B1. So how do we interpret B1? B1 measures the approximate percent change in y hat for a small percentage change in x. For instance, if y represents the quantity demanded of a particular good, and x is the unit price, then B1 measures the price elasticity of the demand. In more details, suppose B1 is negative 1.2. The B1 was negative 0.2. So how do we interpret this in this kind of model? A 1% increase in the price of the goods, so 1% increase of the price of this good, which is x, is expected to lead to about 1.2% decrease in its quantity demanded. So 1% increase of the independent variable leads to about 1.2% decrease in the response variable. Log-log is nonlinear in its variable, but it's still linear in the coefficient, so we can use it in the linear regression. It satisfies the requirement of the linear regression. And these are the graphs, how they look like when beta is between 0 and 1, when beta is less than 1. The second part we're going to discuss, which is when we have the log on the x on the predictors, not on the y's, not on the response variable. So we take the natural log or the log of the dependent variable and keeping the response in their original form. And the same thing, the interpretation here. The interpretation is important. So how to interpret this, especially B1? First of all, the model takes this form. The estimated model takes this form. How to interpret B1? B1, if you multiply it by 0.01, measures the approximate unit change in y hat when x increases by 1%. For instance, if B1 equals 5,000, then a 1% increase in x leads to a 50 units. How we get 50? Because 50 times 5,000 times 0.01, we got 50 increases in y hat. And again, this is the graph of the model. The last one is when we have the logarithmic only applied to the y, when we do a transformation on the y, not on the x. So the first one, log on both. Log on both of them. Semi-log regression model on x. The log is just on x. The exponential, the log is on y. And how to interpret the b1. The b1 times 100 measures the approximate percent change in y hat when x increases by 1 unit. Okay. The exact percent change can be calculated using this formula. Example, if b1 equals 0.05, that means a 1 unit increase in x leads to an approximate 5% increase in y hat. And as you can see from these models, it seems that we are using these models or reapply these transformations if we need kind of percentages change interpretation. If we need this kind of interpretation and having percentages to percentages or percentages to units or units to percentages, then that means we may go for the one of the logs regression models. After this, we're going to discuss example for each case of the regression models we discussed.